All right, so remember what we've been doing? We've been doing, we left off doing analysis of variance for simple regression. And I said the reason we were doing that was we were going to look at a general way to do hypothesis test for more complicated models than just having one X variable. So now we're going to have more than one predictor. So and the simplest way, I think, to introduce multiple regression is to just introduce a super simple predictor that's a binary variable, a 0-1 variable. Okay? So, and also it's a good way to see how to control for a confounder in a regression model. So, so we're going to be including this binary 0-1 variable, in this case gender, whether you're male or female, in a regression model. But let's just remember back to part two about causation and confounding. And we talked about, in part two, how there are two ways to control for a possible confounding variable in observational data. And we looked at stratification as the first way, and then we talked about modeling as the second way, and that's what we're going to explore now. So including a likely confounder as an independent variable in a regression model is one of the main uses of multiple regression. And now we're going to look at the simplest case of adding a binary variable to a simple regression model where you have a quantitative X predicting a quantitative Y. Okay, so on our STAT 100 survey data, we saw this negative correlation right here between what? Between how big somebody's foot was and the number of shoes they bought. And we saw this negative correlation saying, the bigger your foot, the fewer shoes you buy. And this we saw back on page, this was in page 19. This is exactly the same thing as back in page 19. We can check back there. Why don't we just look back just to refresh your memory, okay? And we go back to page 19. And this was when we were talking about correlation confounders. And you see, remember this? And we saw this negative correlation. And we said, does that mean that the larger your foot, the fewer shoes you're going to buy? Is that a causal effect? Why would that be? And then we thought, maybe there's a confounder, gender. Males have larger feet and they buy less shoes. Or we could have said females have smaller feet and they buy more shoes. So what we did here was we said, okay, the way that we control for this is by stratifying. If we think that this is gender is a possible confounder, we're going to split the data into two groups to remove that where the confounding variable is the same. Just look at men alone. And just among men does the bigger your foot correlate with the fewer shoes you have. And just among females does that hold up. So we just sort of thought about it, and I said, okay, so we just drew this basic picture that we have this when we're looking at the number of shoes somebody has, it's confounded because the people who have small feet are also females, and they tend to buy more shoes. So we want to separate the effect out of the size of your foot from whether you're males or females. So we did that by saying, okay, look just at males, just among males. And then does the size of your feet, whether you have small or big feet, does that really affect how many pairs of shoes you own? And we looked at the data, and we said, no, it doesn't. It just among males, it hardly makes a difference, and just among females, it hardly makes a difference. We're seeing this effect because of the confounding effect of gender. All right, so now let's go back to where we are. And now we said that, okay, so let's look at the data here, and I'll show you. So here's the data of everybody together, males and females, and then if we split, and the idea is, we see this in observational studies, right? And we say, does your shoe size, how large your foot is, as that goes up, does that really cause your the number of pairs of shoes you have right here, the number of pairs of shoes to go down, the number of shoes to go down? That doesn't seem likely. Or, right, is there some kind of confounding variable, in this case gender, that we're thinking of, that's really causing males are down here with big feet and not many shoes. So that's what's gender's driving the shoe number, or females are up here with smaller feet and more shoes. And gender is both driving the shoe number and driving the size, the shoe size. And when we split the data, you can see what happens is this negative correlation, which was what? How big was this? This is a fairly large negative correlation of negative 0.3289. That's a pretty big negative correlation, right? It's very significant, actually. And then and you see that strong negative correlation, look what happens. It pretty much disappears, and there really isn't much correlation here. This is just among what? This is so hard to see, but these are the males, and these are the females. And when you split them along the confounding factor, right, so you're taking that out of the picture, right? Everyone here is a male. Now, does the size, how many shoes, no, is this the size of your, this is your size, your shoe size, right? The bigger your foot, does that still affect the number of shoes, number of pairs of shoes? Doesn't seem to. And here, it doesn't seem to either. Does your shoe size affect the number of shoes? No. So when we split it, and the basic, it disappears. And the basic idea is this. I mean, I'll draw an exaggerated version of this, is that we have two groups of people, right? So we basically have a graph here, where here's your shoe size, the size of your foot, and here's the number of pairs of shoes here. And we have two groups of people. I'm going to do a super exaggerated version. We have the females. I'll code them as like Fs. Little Fs up here. Imagine all the females here. We have lots of females. And then we have males. I'll make it really exaggerated. Pretend each one of these is a male, and we have hundreds of these. Okay, lots of dots down here. And then when we combine them, we get a negative correlation, right? A negative correlation. Even though within each group, there isn't a negative correlation. That's confounding. Do you understand? There's no negative correlation within each group, but when we put them together, so when we separate them into two groups, I should have put the females here. Would have, if I separate them into two groups and I put the females, this is females only, and males, within each group, there's no correlation, but when you put them together, you get that negative. Does that make sense? You could even have a positive correlation within each group. You could have it look like this. Pretend there was a positive correlation within each group, right? When we put them together, you could still get a negative. Does that make sense to everybody? All right, so just to show you this picture here, we've got this picture now, and let's look at it on our data, because we're going to be exploring this data. You're going to be using later on, you're going to be using this data program, so you might as well get the hang of it, and you might want to explore it yourself. So let's go to the PC, and on the next page, there are directions for finding this data set, and let's look. So you can go to the data program, and it says to, first you want to choose the Stat 100 data set, and you're going to choose a data set here. And it says to choose, on the next page, it says to choose this, what is it? Survey 1 combined from spring, this one right here. It's kind of hard. This is the one you want to choose. And we have all these variables here. Now, the scatter plot we were just looking at, you can go to scatter plots. And what were we doing? We were saying, okay, the shoe size, predicting, that's our x variable, predicting what? The shoe number. And there is our graph. And here is the same correlation coefficient you see back on page 53, negative 0.3289. And here is our regression equation. The number of shoes, the predicted number of shoes is equal to this intercept minus the slope of 2.154 times the shoe size. All right, and here is the regression equation. So it looks like we're not doing a significance test here, but if we did do one, it would be very significant. Now, and here are the statistics. So you can see there's 1,046 students who responded to this survey, and this is what it looks like. All right. Now, let's split the data into two graphs. And that's what you're seeing at the bottom of page 53. Here's, for males, it looks like this. And for females, it looks like this. And it looks like, look, the correlation shift was, there's not much correlation. That's what I'm saying. Once you remove the confounding effect of gender, that correlation of negative 0.3289 went almost to zero. And it changed actually from negative to slightly positive. All right? A little bit stronger for females than for males, but neither of these are significant. So it's basically flat. We didn't get completely zero slope. Closer to it here, we have a slight uprise here, but nothing really of importance. Now, watch what happens. You can get a kind of a feel for what happens if I combine the graphs again. And here what I did is I colored, there's a lot more females in Stat 100, so all these purple colored dots represent the females, and the yellow ones represent the males. So this is what it looks like when you do it together, and this is the regression line that you saw. We're just combining them. So you're going to see one regression line for females and one for males when I combine them. Okay? And they're not quite exactly the same slope. There's still a tiny, tiny effect, but it's not significant. They're not exactly the same. They're not exactly flat, both of them. This one looks a little bit higher than that one. If I force them to have the same slopes, like that has this regression right now. This is basically the same thing as doing multiple regression, which is where we're headed, without an interaction term. What we're going to do is we're going to build a model with two x's, an x for two x variables. One's going to be for gender, just a 0, 1 variable, and the other one is going to be our usual, the same one. It's going to be the size of the shoe. One's quantitative, and we're going to build a model with that. And it will give us basically it will give us these two equations. Not quite the exact ones we get when we split. If we wanted to, we'd have to include another variable that would allow for different slopes called an interaction term, which is chapter 13 if we wanted to do that. So that's the basic picture of where we're headed for today. I'm including this because I think we might be able to get to chapter 13 today as well. We'll see. All right. Now let's go back to the document camera, now that you understand that. And so So we suspected doing this right here is called stratification. We suspected gender was the likely confounder, causing both females to have smaller feet and to have more shoes, or males to have larger feet and fewer shoes. So we broke the population into two groups along that confounding factor and saw the relationship disappear. Gender was the confounder. So we refer to this, we call this stratification. We're stratifying along that confounding, that's stratification. And that's what we did in part 2, okay? Nothing new here. These slopes are almost zero, but not exactly. And this is the same as, this was the same as page 19, and this is the same as page 20. Stratification, page 20. Where should I put this? So this is like page 20, and that's like page 19. All right, now what we're going to do is modeling. Now let's look at how including gender, a 0-1 variable, as an independent variable, that means a predictor variable, an x variable, predicting y, which is the number of shoes people own, along with shoe size, that would be another x, right, would also work to separate out the effects of each. So we're seeing how including another variable is one of the main purposes of multiple regression, to control for a possible confounder. And that's called modeling, building a model to control for, instead of just stratifying. And that's going to be a lot of what we're doing in this, a lot of what multiple regression does. Whenever you see, oh, we controlled for this variable, we built a model that controlled for this, and controlled for that, and controlled for that, this is what they're doing. They're including them as independent variables in the model to separate out the effects of that variable from the other ones. Otherwise, they're all mixed together, confounded, right? So first, let's carefully look at how to, but now, the simplest, I mean, this is a very simple model to include a binary variable, but first, let's look carefully at how to interpret the slope of a binary predictor variable, because I don't think many of you have done that before in a regression by drawing the scatter plot of gender, just that 0-1 variable, male or female, predicting the shoe number. So that's what we're going to do first. So let's go to this page, and we'll go to that same data set, and that's what I do here. I think it's easier to look at, why don't we just scoot right back to the where I got this from, so we can, it's a better display. I can see it better, and then we can go back here and work on it. Okay, so here we are, and now, first of all, we're not having the split plots anymore. Okay, so we're just here. Now, instead of choosing our x variable to be shoe size, I'm going to choose it to be gender. And this simple, if you're in 3D, you can only have one x. We'd have to go into, if we want to go have two predictor variables, we're going to have to go into 3 dimensions, and we won't be able to have a flat scatter plot like that anymore. It won't even, this program won't allow us. We'd have to go to a different option in this program. So now you can only have one variable, and now we're saying we are going to use this categorical variable, gender, and we're going to code it as 0 and 1, so these numbers are meaningful, 0 if you're a male, 1 if you're a female, and then we can just do a scatter plot. So there's nothing wrong. You can easily do if you have a categorical variable, this is perfectly legitimate to do this. So now we have a scatter plot like this that says, okay, here's all the men, and here's all the women. And we coded the men as 0, we coded the women as 1. And what is this regression? Now we have a correlation, a very strong correlation, and it's positive, only because I coded the females as 1, right? It's a positive correlation here. And what is this regression equation doing? Well, it's saying that if you're a male, I'm going to predict the average for men, which is 6.8. Here, I'll show you. If I split this into two graphs, you can see the average number of shoes for men is 6.884. The average number of shoes for females is 19.74. All right? So now if I put them back into one plot, what I'm getting here, right here, this 6.884 is the average for males. And then if I go over 1, what's the slope saying? If I go over all, from 0 to 1, how far will I go up? I'll go up 12.86 to the female average. So the female average, so that's the difference between the male and female average. Together, they add up to the female average. Here, you can see this really easily. Let's go back to the document camera and just work it out here. All right, so here's the same plot, and here is gender, and these are the males, only because I coded them that way. Okay? We're going to reverse the coding and see what happens, but for now, let's leave it this way. Males are 0, and females are 1. Okay? Now, these are all the females, and their average, I should have put a Y here, it's the average, this is Y, the shoe number, and this is X, whether you're male or female. So what I want to say here is the average number, Y bar, the average number of shoes for the females equals 19.74. And that's this. So if you're a female, my best prediction for you is the average, 19.74. And if you're a male, Y bar for males, that point right there is 6.884. And the difference between those two is this slope. It's hard to read that regression equation. This says the predicted number of shoes is equal to 6.884. So Y equals the male average when Y, okay, so when X, which is gender, is equal to 0, you're a male. When X is, okay, so if you're a male, X is equal to 0. So that's your equation. And if you're a female, X is equal to 1. So that is, what's this 12.86? It's just the difference between the male and female average, right? It's just the females minus the males, right? So when X is equal to 1, you get the female average. Let's do it right here. It's much easier to see. Okay, so what does the regression equation give for males? Let's just look at that. What does it give for males? Y equals 6.884 plus 12.86 times what? X. And X is what when you're a male? X is 0. So that's what you get. Does that give what we want? Yes. That gives the male average. That's what we want. The male average number of shoes. Now, how about when you're a female? What does this equation give? So that's 6.884 plus 12.86 times what? 1. And that adds up to 19.74. Does that check out? Yes. It gives the female average. This is hard to read. I'm really sorry. This right here is the difference between the male and the female average. And this right here is just the male average. Questions on that? Okay, so what if we coded it the other way? Could we use this equation? If we coded it the other way, and X is now 0, if you're a female, okay? So if we switched this coding, and if you're a female, this disappears. Is that going to give you the right equation? Is it? No. So what do we have to do? What would we do? We'd have something, the intercept, right, plus a new slope times the gender, and let's just fill these in. And what I say, x is equal to 0 now, and x is equal to 1, but we're switching it. So this is for females, and this is for males. All right, now, what should I write in here? Any suggestions? We know this 6.884 isn't right. Now, for females, let's say, let's start with whoever's coded as 0 is the simplest because that disappears. So we want the female average, so what should I put in here for the intercept? 19.74. Yeah, yes, exactly. So we'll do that, 19.74, because that's the female average. Let's write that in. All right, now, that's fine when we have a 0 in there. Now, let's say we have a 1 in here for males. Now you're a male. So what do you want to end up with? Let's think. So we want to end up with what when you're a male? When you're a male, we want to end up with, we want to get rid of that. This is going to be a 1, right? So we want to end up with the male, right? That's what we want to end up with, right? But we already have that, so what do we have to subtract off? Yeah. Mm-hmm. So this is what we want in there. And if we do that, 6.884 minus 19.74, what do you think we get? It's the difference between the two averages, and we're going to get, when we do it, we're going to get negative 12.86. Just the opposite. It's still the difference, but it's just in the opposite direction because now the females are coded as 0. Does that make sense to everybody? So the picture would be, just think about this, is switching this whole column and putting it here, and switching this column and putting it here, and then we'd have the same, we'd go from 19, be going downhill the same amount. All right? So that's the idea of the binary variable. It's super easy. All right? So you can code either one as 1, but you just have to, that's going to switch. And whenever you have a binary, what do I mean by a binary variable? I mean when you can divide the population into 2 groups, like male, female, or dead and alive, or yes, no, any of those things. All right? By the way, if you have a binary variable as your y variable, which happens all the time, because often you want to predict whether somebody's going to live or die, let's say, then your binary variable would be here as a 0, 1 variable, and often you'd have quantitative predictors, right? That's called logistic regression, and that's what we're going to do towards exam 3. We'll cover logistic regression. So that's when the y variable is 0, 1. Now we're focusing on having some x variables 0, 1. All right, so now we're ready to put together 2 simple variables into one equation. And now we're going to try multiple regression here, and let's think about it. All right, so now we have these 2 simple regression equations, right? The one we just looked at, predicting shoe number from whether you're male or female, just given the averages. That's the first one. And then we have the one from predicting, we're predicting the same thing, number of pairs of shoes, but this time from your shoe size. So we have 2 of them. This is the one we just did. Remember, this is the male average. That's the one we just did, this one. That's one of them. And the one we started our hour with, we didn't, do you remember this one? This is just like the negative correlate. This is like, let me show you. This is this one right here. Right here. It's this line, okay? Now, so we have those 2. They're both called simple regressions because they have one x 1x predicting 1y. 1x predicting 1y, the same y. Now we're going to combine those two predictors, these two, there's going to be x1 and x2, into a single multiple regression model. And it serves almost the same purpose as stratification, as drawing two separate scatter plots for males and females. Almost, I'm saying. It's not exactly the same because you'll learn in a minute, but it allows us to separate out the effects of each variable. All right, we're separating out the effects. What we want to do, since these were confounded before, since gender and shoe size are correlated, right? And you can even see how strong the correlation is. We should look at that. That's right here. They're correlated. That's the correlation. They're only positively correlated. I coded males. I coded females as 1, and they have more shoes. That's why they're positively correlated here. But they're correlated, right? Because females have more shoes than males. All right. Excuse me, they're correlated because females also have they're correlated because, I said that wrong. They're correlated because females have a smaller foot. These two variables, shoe size and gender, are correlated because females have a smaller foot. And they're confounded because they're also correlated with the number of shoes. All right. Now, so here's our multiple regression with a binary categorical variable and one quantitative variable. And it looks like this. So we're predicting the number of shoes from an intercept. And here's the gender. That's x1 is gender, and x2 is shoe size. All right. Any questions so far? So, now, what are we doing here? Do you notice this is saying that both the males and females have to have the same slope. We're just getting one regression equation. Before we look at this, let's look at the regression equation that we actually got when we did it. I got this from the computer by doing a least squares fit, and this is not the equation of a line. This is an equation of a plane. So it's the best fitting plane to minimize the sum of the squared errors. That's what we're doing here. And here we have the slope, and we get the focus right here. I want to first get the equation, then we'll look at it, okay? So right here is your equations, and you have an intercept. The intercept, I'm looking right here. The intercept is 4.255. There's your slope for gender, 13.51, and there's the slope for shoe size. So that right here is our multiple regression equation with two variables. Now, let's focus back up on here. And what is it saying? It's saying, let's look at shoe size first. It's saying this slope. You see, first of all, look at this slope. That became pretty small, right? Pretty small compared to what we had up here. Here, we have a slope. Look at the difference between these two. Here, we have this really first of all, it's negative, and it was very significant. It had high correlation, right? Now, we look at it, and it's a much weaker effect. It's in the wrong direction, and it's not even significant. This is what I'm saying. This slope right here, oh, so sorry. This slope right here, is that significant? Look at its p-value. Is this significant? No, it's not even significant. is the slope for gender significant? Let's look at that one. That's right here. The slope is, let's compare it to the here. It's not that much different. It matches up with this one in the simple. It's a little bit stronger, a little bit bigger. And look, it's extremely significant. So this is very significant. So what that's saying is very similar to what we saw before, that this slope doesn't really matter much. It's not significant. Its gender is the driving force that's determining the number of shoes. Now, it didn't go all the way to 0, and but it's not significant. Okay, so let's focus now again. And so what do these slopes do? The slope of, first of all, you can see they're not the same. These slopes in the multiple are different than the slopes up here. All right. Now, the slope of each predictor in the model controls for the other variable. It controls for the, here's another use of the word control. All right, controls. So it means that, what does it mean to control? It means it looks at the effect, for example, for gender, it looks at the effect of gender controlling for the other one, which is shoe size. So for people who have exactly the same shoe size, let's say males and females who have exactly the same shoe size, then it says how much being one gender over the other is going to affect the number of shoes you have. So if you look at males and females who both have size 10, right? This effect of gender is very strong. It says for the same shoe size, you're going to have 13.51 more pairs of shoes on the average for girls than boys. So that's why that's a big effect. All right, now what's this one say? What's the slope for shoe size? The slope for shoe size is small and insignificant, but what's it saying? It's saying that it estimates how much an increase in shoe size affects the predicted number of shoes for those of the same gender. So if you're all males, does having a bigger foot affect how many shoes you have? Well, it's saying it has a tiny little effect, but it's not significant. So this little thing right here is similar to this effect, which was almost nothing. It was a little bit stronger for female than for males, and there's more females when you combine them. It forces them to have the same slope here, but this is pretty insignificant, whereas the other one dealt with this. It's very significant. Okay, so that's how we combine them. So now I think you'll understand it better if we say, what does the above multiple regression equation simplify to for males and for females? So let's try that. So for males, what does it say? So let's do males. And remember, males has x equals 0. So what do we have? We have y hat equals 4.255 plus 13.51 times 0. So that cancels out. Plus 0.2472 times the shoe size. All right? Times x2, which is the shoe size. Now we'll do the same for females, and now we have x equals 1, and we say what? We say this is equal to 4.255 plus 13.51 times 1. That's the difference due to being a female. Big difference. Plus 0.2472 times x2. And a tiny little insignificant effect that's positive due to the number of shoes you have. So what it does is it forces these two to have the same slope. And in this case, it wasn't such a bad idea because both slopes were very close to 0, and we didn't really care about that. So what's this together? This together is 17.765. And if you looked at the average for guys, they're about 10, the average shoe size. So if you add 4.255 plus 2.472, it was about 10. You get about 6. You get about the average there. And if you do the same for females, I think the average was 8 here, plug in an 8, about 8 times that plus this, you'll get about 19.74. All right, now let me see what else I want you to look at here. So when we combine them, we got this multiple correlation coefficient that I haven't told you what it means yet. 0, and we got an r squared. And you can see this is your regular ANOVA table, and you should be able to match it up the way that you always do with, what do I mean match it up? Make sense of it. So your sample size is 1046. The total degrees of freedom will be 1 less than that. The number of parameters here is what? Where is our model? The number of parameters is we have 2 slopes and 1 intercept. So there's 3 parameters. It's right here. We can do here. So this is 3 parameters, right? And we have n equals 1046. So you can see that these work out, right? This is n minus 1. This is p minus 1, 3 minus 1, 2 slopes in the model. And this is n minus p. 1046 minus 3 is that. And they add up. And the structure of it, you know, r squared times your sum of squares. This is your sum of squares model. This is your sum of squares error, sum of squares total. And here's your F statistic, and you can see that you could verify that, for example, the chi-square statistic is what? R squared over 1 minus R squared times that. That's how they got that, etc. But before we do that, I think we should look at, why don't we look at the homework you have to do, okay? I want to make sure, I want to see if we have to go on and do interactions for you to understand the homework or not. So let's look at the homework I just posted. I want to see, make sure you know how to do it without further explanation. So let's just see if you can work on it together in class. Just the first problem. I'll randomize it, so it won't be what you get anyways. So let's look at it. All right, so let's go to ln kappa. And I just want to see how it makes sense to you. I don't know what happened here. Okay, here's the first problem. I better make sure it's randomized. Let me just go to the, hold up. Okay, let me just see if the numbers change for sure. Yeah, okay, so it's all randomized, we're good. So let's just make sure you know how to do this. So the scatter plots below show 2 groups of data distributed in 4 different ways. okay? Distributed in 4 different ways. They're color-coded. One group is red, the other group's blue, just like we have the males and females, right? Group A data are drawn in red and group B data are drawn in blue. Regression lines for each group are also drawn. The overall simple regression line for the combined data is drawn in green. So when you combine these two together, you get this negative correlation here, even though individually they both have positives. Okay. And in some of the graphs below is misleading because it doesn't take into effect the confounding influence of group membership. Your job is to find the overall multiple regression equation that does take group membership into account and yields exactly the same thing as the 2 separate simple regression equations. Now, in our example, I didn't give you the 2 separate simple equations because in real data, it's not going to be exactly the same thing unless you include an interaction term. In other words, I'm saying these 2 slopes are exactly the same. In our data, on page, if you turn back to your the very first page that we looked at, 53, and I split those two lines, I didn't give you the exact regression equations for them because they weren't exactly zero. Those lines aren't exactly 0. They're not exactly the same slopes. All right? So once we do include an interaction term, you will get exactly the same thing. But I just want you to show you first, in this case, I think it's really helpful to just, that's why I gave you these not real data. I just drew 2 groups that have the exact, in every example, they have the exact same slopes, right? Exactly the same slopes. And I want you to come up with the multiple regression equation for them. So I just want to make sure that you all know how to do this. So why don't you just take a few minutes, like right now, think about this problem. And it's very similar to what we did before. You have to look at group. How is it coded? That's the key, right? So we have to translate these. First, you have to figure out which group is coded as 0. And did I tell you which group is coded as 0? Group, where does it say it? Right here. Assume that G is a 0 coded with group A. Which one's group A, red or group A? Okay, group A is coded as 0. All right, so group A is coded as, oh, here you have it right here, yeah. So I think you know how to do this. It's just like what we did before when we were figuring out at the beginning of the hour. It's a very similar idea. Do you want to try one right now? Do you want to try it? If you have your own like homework, you could just go right to it and try it on your own, or we could do this one together. Why don't we do one together to make sure? You tell me why don't we do this one all together? Okay? Think about it. All right. So the hint says fill in the intercept and to fit the group A. So we want when this is 0, it's much easier to start with, okay, so when this is 0, we just have this equation. So what do you think we should do here? What should we fill? When this is 0, we want this equation to get what? Which one is 0? What should I put in here? What do you think I should put in here? What number? 5.2. You think that would work? And then what should I put in here? Say again? 1.7. Okay, so why are we doing that? We want to make sure it matches what? It matches when G is 0. So it matches red right up here, group A, because we coded that as being 0, right? Group A is 0. So does that work for group A? Now you have to figure out when this is 1, how we're going to have to adjust that to fit for the other one. Do you understand? When group 1, we want it to fit that one. So what are we going to have to do? put in there. That's the idea. I think you can get that. You can think about it now. What do you want to get? Just think about it this way. It's really easy if you think about it this way. What you want? You want to get that equation. Do you already have the 1.7x? We already did. So we're just trying to change this to what? Negative 4.15, right? I want a negative 4.15 inside there. Now, is that going to work? I want it, if I didn't have this, if I erased this, it would be great. It would fit the blue. So all I want to do is get rid of that. So what should I subtract off? Right? That's not, I have the 1.7x, but 5.2 minus 4.15 is not minus 4.15. So I have a 5.2, so I want to subtract off a what? 5.2, right? That's all you need to do. Does that make sense? So that's, I shouldn't have done it for you, but I was worried that I didn't give you an example like this. I'm not going to do the rest of them, but. Okay, does everybody feel comfortable with that? Questions about that? So the reason I didn't do that in class, I did it with the I didn't do the exact analogous thing because we didn't have exactly the same slopes in our example. Let's see what's next. I'm just curious what's next here on our homework. So let's go to what's next. Oh, this is a conceptual problem, more or less. Okay, let's see what's next. I have this too. I posted this, and this is very similar to what we just did with the, it's about sumo wrestlers and NBA players. And you get, usually when you do height and weight, you get a positive correlation. But here, you're going to explore this data set, and you're going to see you don't get a positive correlation. Why? Because you have these two groups of people. One of them are shorter and fatter, and one of them are taller and thinner. And they're two different groups of athletes, sumo wrestlers and NBA players. So you're going to look at that data set, and then you are going to look at, and you'll be able to do this, and then you're going to look at interactions. You know what I might do now? What I might do is just, it's Thursday. We could go on. Do you want me to go on and do chapter 13? I didn't do it for the other class. Do you have any questions? I know what we can do. How about we do this? Let's look at our scatter plot where we were. And I didn't show you how I got that ANOVA table. Or how to even do that type of analysis with our data program. So let me show you that. So I'm going to go home to our home page, and let's just quickly go back to the document camera so I can show you what I mean. How do you analyze this multiple regression using an ANOVA table? Where did this come from? All right, so let's look at our, I'll show you where that comes from. And we're going to explore it in a lot of detail when we get to multiple regression. But I just want to show it to you now. So we'll go to the computer. And we're going to go to away from scatter plots and to regression. First off, can I do a scatter plot? Let's go back to scatter plot and see if I can even do. Can I do a scatter plot with gender and shoe size predicting? No. So do I have any 3D scatter plots here? Yeah, there is a 3D scatter plot, so I can show you what that looks like. Because now, as soon as you have two x's and a y, we've got 3 points that determines a plane. Do you see that? Do you see the, maybe if I show you the plane, why don't I just show you the regression plane? That'll make it a lot easier. Okay, so here's the equation for the plane that we got. And I think it's much easier if I showed you this. Do you see how there is a slight effect, a tiny, tiny little effect for the shoe size, but the big effect, this diagonal line right here. Do you see how the plane tilts up? That's for gender. Because the average for females is so much higher than the average for males. See how it's intersecting right there? Up at the, see how that's a big slope. That's our big slope for gender, and this is our little slope for shoe size. So you can play around with that. But now we're going to go to, let's say you wanted to analyze this. So you would go to regression, and what would you do? You would choose your variable, your y variable, which is shoe number, and now you're going to choose gender and shoe size. And now you've got, you could do chi-squared test. You could do an ANOVA table. Here you can have your slopes as z statistics. You could do them as t statistics, whatever you want. Now, let's first look here at this chi-squared. And you can see that the way that you could get, once you know this r squared over 1 minus r squared times n will give you that chi-squared. Now, what is r? What is r? Because r is, it can't just be a correlation coefficient, because a correlation coefficient is only defined on 2 sets of numbers, right? And now we have 3 sets of numbers. Everybody has 3 numbers associated with them. Everybody has how many shoes they have, the size of their foot, and whether they're 0, 1, male or female. So how do you do a correlation coefficient between 3 sets of numbers? So what that is, what that r is the correlation between these 2 sets of numbers. Your actual number of shoes, the y variable, the actual that everybody has in the class, and the predicted number. And obviously, the stronger that is, the closer your predictions are to your actual. If they were perfect, you'd get an r of 1. So it's just it's another way to figure out a correlation coefficient, and it's equivalent to what we get in simple regression. I mean, you could compute, you'd get the same correlation coefficient, except it would always be positive if you looked at the correlation between the observed values and the predicted values. So that's what that r is. You're going to learn a lot more about this when we dive into multiple regression with lots of variables. This is just a preview mostly to help you understand the idea of controlling for a confounder. But that's what that multiple r is. Multiple, and it's the same exact thing. This, in simple regression, is just the positive absolute value of your correlation coefficient. It has to be positive because you're looking at the correlation between your observed and your predicted. And you never predict, you're always going to have a positive correlation between what you predict and what you observe. Even if it's a negative correlation between the 2 numbers, your predictions are going to be close to what you observe, the same sign. So that's that. Just so you can read this and explore this, I mean, if you're all stats minors, or a huge amount of you're going to be using stats in other classes, there's no way you can just absorb everything from lectures. You've got to dive in and look, explore, play around with data. And so see if you can figure out what's going on. And this data program, the reason we designed it is for pedagogical reasons, so you can just jump right in and just play around with it and look at data and just choose any variables you want. You can just see what happens. But I just wanted to show you and look at the relationships. You can choose the F and the T. You could do re-randomization. You can do a whole lot of stuff. And so how would you get this F statistic from this? You could do the same thing, r squared over 1 minus r squared. But then you'd have to multiply by what? Not n, but n minus the number of parameters, 10. But then you'd also have to divide by the degrees of freedom in your model, too. And that's why this F statistic is about half as big as this, because we have 3 parameters now, see? So that's a jump ahead for what we're going to be doing later, because we have a lot of time left. So I just wanted to explain that. This isn't what your homework's about. This is just like a little preview. Yeah?
So we are going to be diving into like
three what? 3 variables, you mean, predicting? Oh, yeah. I mean, here we already have 3 variables, right? We have 2 predictors. But yeah, we can have as many predictors as we want. I mean, we can do it right now. I mean, just click on another predictor. But I just want you to understand, like, what else do you think would predict shoe number? Maybe weight. So we could add another predictor. Now look what happens to this chart. Now you have 3 slopes. 1, 2, 3. Predicting. So you're going to have degrees of freedom are going to be 3 for your model, right? And now I bet this F statistic will be about 1/3 as big as that. But that doesn't affect the p-values. So you're going to learn all about this. You're going to, I mean, you could put whatever. Do you think pets? No. Pets.
It's a 0.35% p-value.
So let's see. So what's significant here? Things are going to drop out. This is what you're going to be doing when you look at model building 2. Like what became significant? Weight is not significant. Shoe size is not significant. You want to put pets in and see if it's significant? Oh my gosh! Now why is pets significant? See, this is crazy. Why would pets predict? This is so much fun. Why would pets predict the number of shoes? Go ahead. Why do you think? How'd you know pets was going to be?
No, I tried it.
Oh, you're just, this is what I mean. This is like, instead of like, R is fantastic, but this is fun. And then you can program stuff in R. But why?
People with more pets might need shoes, like need more types of shoes for like whatever they do with their pets. I don't know.
Okay, so he's
Maybe
saying
they
if
love
you're,
nature more.
oh yeah, you walk your pets, so you need walking shoes.
Right.
They shit on your shoes, so you need another pair of shoes. Sorry. I shouldn't say that. But pets are messy. They get hair all over your suede shoes. Okay, but what do we want to do? If that's true, let's just take out some of these variables. I want to see what happens. What about pets alone? So let's just take everything out. I mean, this is what this data program's for. This is what I mean, play with it. Good. Now, yes, pets is a predictor on its own. It has that. And what's the correlation? Oh, my gosh. Now, what if we do pets and gender? Wow. So they're both predictors now. And what's our R squared? Our R is what? So this, what was pets alone? What was our R? Pets alone, what was our correlation? Oh, it's a small correlation, though. It's significant because, remember, we have a very tiny we have a huge sample size. We have an enormous sample size. So remember I said any tiny little. So, you know, it might just fit some accidental feature of this particular data. I wonder if it holds up. So you know what we should do? Watch. Let's go to another data set. I ask this all the time. Let's go to your data. See if pets is a predictor in your data, okay? So what's your data? Your survey 1, fall what, 16? Where are you guys? I don't even see it. Survey 1. Oh, yeah, it's not in the set. You've done some exploring here, right? So it's not. So we'll just choose basic data set. Let's look at your data sets. Okay, so it's survey 1, right here, 200, this one. All right, let's see in your data set if it is. So let's go to regression, and we're going to choose shoe number, pairs of shoes, and we're going to look at pets. You want to bet? I wish we had eye clickers we could do about. Hey, you're leaving. You asked the question. You put your bet back here. Sorry, I mean, no, really. You asked the question. You don't get to leave.
I got an advisor appointment, man.
You have a what?
An advisor appointment.
Okay, let's do a vote. Do you think he should be allowed to leave? Do you think, okay, all in favor say yes. All against say no.
Yes.
Okay, since it was a tie, I'm going to say you can go.
Sorry about that.
That's okay. Great question. I'm giving you a hard time here. You know that. I like teasing people. Okay, you're good. Yeah, and thank you for asking that question.
So this is all, we can all get to the 3D stuff too, mess around with that.
Yeah, you can get to it. And I encourage you to. Okay, see you. Bye. All right, you too. All right, so, but he'll never know the answer unless he does it himself. I'm so curious. So, do you think it's going to be significant? Pets? No, it's not. It's not significant. We have a much smaller. Let's try it in Stat 100, though. And then, this is so much fun. All right, So now we're going to go to Stat 100 data set, and because they have a much bigger sample size, the same one this semester, and it's right here. And now we're going to do the same thing, and now we'll see if pets. So choose your Y variable, shoes, number of shoes, and now we're going to choose pets. Whoa! It is significant. It's very small again. Small but significant. Why? That's so interesting. So we have a very small effect, but it is significant. It's held up. I wonder if it holds up through all the data sets. Have you looked at different ones?
I'm looking through each of them like one at a time, and it holds up almost all the time, but not quite all of it.
It holds up all the time. The number of pets. Does pets by itself correlated with gender? Let's see. So let's do gender. I don't think it is. But let's just choose a different Y variable, gender, or doesn't matter. I want to see if pets is correlated with that. No. Shoe size. Slight difference of like, interesting. Huh. Wow. Very interesting. Well, that's a really cool project to think about. Okay, guys, so have a great weekend and have fun exploring the data.